So in this video, we'll be looking at the reactions of alkenes, alkynes, and aromatics. And we'll start with alkenes and alkynes, and we sort of group those together because they often have similar chemical reactivity. The first reaction that we'll look at is catalytic hydrogenation. And then what we do is we mix our alkene or alkyne with a hydrogen gas and a catalyst, oftentimes a platinum or palladium catalyst. And these metals will bind to the hydrogen gas and to the alkene and help that reaction between the hydrogen and the alkene go forward. That's why it's a catalyst, that it helps the reaction proceed. And so what happens when we do a catalytic hydrogenation is we add hydrogen across either the double bond of an alkene or the triple bond of an alkyne. And so if we start with ethene, so this is ethene, two carbons double bonded to each other, and we do catalytic hydrogenation. So we're adding hydrogen gas to the reaction and a platinum catalyst. Then this will react to add more hydrogen atoms. And so we'll go from having 2 hydrogen atoms on each carbon to 3 hydrogen atoms on each carbon. And it's the same way if we had ethine, except now we'd have to use 2 molecules of hydrogen. So 2 molecules of this hydrogen gas would react with this ethine to add 2 hydrogens to each carbon. And get us to ethane. And so both of these reactions, whether we use ethene or ethine, will produce ethane because we'll either add 1 hydrogen molecule or 2 hydrogen molecules to convert the double bond or the triple bond to the single bond. And so catalytic hydrogenation converts alkenes and alkynes, converts both of them to alkanes. And so it's a very common reaction where we want to convert double bonds or triple bonds to single bonds. We can do a hydrogenation reaction and perform that transformation pretty reliably. So the other type of reaction that we'll look at is the hydration of alkenes. So double bonds. That a hydration reaction will convert an alkene to an alcohol. By adding water across the double bond. So if we start with ethene again, then let's react it with water. And this requires an acidic environment because the acidic environment, the acidic solution, catalyzes the reaction between the double bond and the water. But anyway, one of those hydrogen atoms from the water will add to one carbon, and then the OH from the water will add to the other carbon. And so we go from the alkene to the alcohol. This is a symmetrical alkene that we can draw a line of symmetry right down the middle. And so it doesn't matter which carbon gets which part of the water. But if we had an asymmetrical alkene, let's say propene, we have 1, 2, 3 carbons, and with a double bond, so this is propene. And we react that with water in acidic conditions. Well, then the hydroxyl group could add to this carbon on the end, and we would get 1, 2, 3. We would get propanol, 1 propanol, or the OH from the water could add to this carbon in the middle, and that would give us isopropanol. So propyl alcohol versus isopropyl alcohol. We could get 2 possible products depending on where the hydrogen atom and the OH group go on this asymmetrical alkene. And so there is a rule for determining which of these products we will get in a hydration reaction. And we'll discuss how it applies to hydration reactions, but it actually applies to a lot more than just hydration reactions. And that is called Markovnikov's rule. And what Markovnikov's rule says is that the hydrogen atom will add to the carbon that already has more hydrogens. And so if the hydrogen atom from the water adds to the carbon that already has more hydrogens, and that means the OH from the water has to add to the other carbon. So let's go back and take a look at our propene again. And let's add the hydrogens just so we can see where the hydrogens are. And we'll react that with water in an acidic solution. Here, let me color code the water. And so if we according to Markovnikov's rule, we look at this carbon here, this has 2 hydrogens. This carbon in the middle has 1 hydrogen. And so, according to Markovnikov's rule, the hydrogen atom from this water will add to this carbon that has 2 hydrogens. So, our red hydrogen from the water will add to this carbon, which means that the OH from the water must add to this middle carbon. And so, according to Markovnikov's rule, this would be our major product. And the other potential product, where the OH is added to the end of the molecule and the hydrogen is added to our middle carbon, this would be the minor product. That we'll get a lot more of this major product than we will of this minor product, because the reaction will favor it will mostly follow Markovnikov's rule and add that hydrogen to this carbon that already has more hydrogens, so that our OH has to add to the other carbon of the double bond. And so we have a few more examples of this. So now we have a double bond where this has 1 hydrogen atom and this has 0 hydrogen atoms. And so when we react that with water, our hydrogen atom from the water will add to this carbon with 1 hydrogen attached. And our OH from the water will add to the carbon that had 0 hydrogens attached. And so this will be our major product. And the opposite product will be our minor product, because this follows Markovnikov's rule, this does not. We can do this with cyclic alkenes. So now we have this 6-membered ring with a double bond and a methyl group. In this case, this carbon here has 1 hydrogen attached. This carbon here on the other side of the double bond has 0 hydrogens attached. And so our OH will add to that carbon with 0 hydrogens, and our hydrogen from the water will add to the carbon that had 1 hydrogen. And so this would be the major product. and this would be the minor product. Again, this is the major product because it follows Markovnikov's rule. So we'll look at this molecule. Now we have 2 hydrogen atoms attached to this carbon, 0 hydrogen atoms attached to this carbon on the double bond. And so that hydrogen from the water will add to this terminal carbon that has the 2 hydrogens attached. Our OH will add to the other carbon of the double bond. So this will be our major product. And I'll ignore the minor product because the minor product is really minor. And one more. We have this cyclic molecule, a 5-membered ring with a double bond and a methyl group, and 2 methyl groups up here, but they're not associated with this double bond, so they won't affect the reaction. But again, we have 1 hydrogen on this carbon of the double bond, and 0 hydrogens on this carbon of the double bond. And so we react that with water in acidic conditions. Then we will add our hydrogen from the water to our carbon that already had 1 hydrogen. The hydroxyl group from the water, this OH, will add to the other carbon. So this would be our major product. And so we can use Markovnikov's rule to predict which side of the double bond the OH and the H will go to in when we do a acid-catalyzed hydration reaction of an alkene. So the Markovnikov's rule is very useful for predicting the outcome of these reactions. So one more set of reactions that I'd like to look at in this video. A little bit about the reactions of aromatic compounds. Then we have aromatic substitution reactions. And those replace a hydrogen with another atom or group of atoms. One of the common aromatic substitution reactions is aromatic halogenation. And so you might think at first that this is similar to the halogenation of an alkane from the previous video, where we react an alkane with a halogen in the presence of ultraviolet light, and we substitute one of the hydrogen atoms for the halogen atom, but that's not the case. In this case, aromatic halogenation does not use ultraviolet light. Instead, it uses iron as a catalyst. And so if we start with benzene, and react that with chlorine, in the presence of iron, then we will add one of these chlorine atoms to the benzene ring. We can do this with bromine as well. Again, it uses iron as our catalyst. And we can add bromine to our benzene ring. So these were all substitutions of chlorine or bromine onto benzene. And so we only get one product, either the chlorobenzene or the bromobenzene. All right, let me write those names down real quick. Chloro, bromo, benzene. So chlorobenzene and bromobenzene. But if instead of using benzene as our starting material, if we used toluene as our starting material, then we would get more than one possible product. So let me show that. So here's toluene. We have this methyl group attached to our benzene. That makes it toluene. So now this chlorine can add here, or here, or down here. And so there are three possible products that can be formed by this reaction. They won't be formed in equal amounts, but we won't discuss why we get certain ones over others. But going back over our nomenclature for these positions, this would be ortho with the chlorine. We would say that this chlorine is ortho to this methyl group. We would say that this chlorine is meta to the methyl group. And we would say that this third chlorine is para to the methyl group. And so we would get the ortho, meta, or para products. Now, if we have a symmetrical molecule, toluene is symmetrical, but it's only symmetrical one way. We can draw a line of symmetry down the middle this way. And so if instead of adding the chlorine to the right, I had added it to the left, it would be the same molecule. We're just flipping the molecule back and forth. And that's because the toluene is a symmetrical molecule. It doesn't matter whether we add the chlorine to the right or the left, because that line of symmetry allows us to do that rotation. But if instead of using toluene, I used paraxylene. So paraxylene adds another methyl group to the bottom. And so now we have a second line of symmetry across our molecule. And what this does is, because now we can flip this both left and right and up and down, it doesn't matter which carbon we add that chlorine to, they're all essentially the same. And so, and let me draw that other line of symmetry in, that we could have added this chlorine to this carbon, or this carbon, and we could show by rotation, just flipping that molecule around, that it's the same molecule. And so if we use toluene for our reactant, we can get more than one product. If we use paraxylene as our reactant, we only get one product. And that's related to the symmetry of the reactant, the symmetry of the molecule, and how these different positions on the molecule are equivalent to each other. So that's it for the reactions of unsaturated hydrocarbons, the alkenes, alkynes, and aromatics that we'll discuss in this class.